Okay, uh, we'll start this topic, theory of equations, for this class. Okay, first of all, we'll start with the fundamental theorem of classical algebra, which states that every algebraic equation has a root, real or complex. So, every algebraic equation has a root, real or complex. So, any algebraic equation has a root, either real or complex root. Now, there's one theorem. Um, an algebraic equation of degree n has at most n root. So, any algebraic equation whose degree is n will have root n number of roots, not more than n. We don't need a proof for this one, okay? Because the proofs are not in the syllabus. Just you have to go through the statements and its applications part. Okay, and there's another one theorem also which says that okay, if you really need a proof, then you can just go through the books. Okay, you can check in your books also. You have got the proof over there, and the proof is easy. Okay, if you don't understand, then you can ask me. Okay, now another one theorem is, if two polynomials f of x and g of x, both of degree n, takes equal values for more than n distinct values of x. Okay, so f of x and g of x both are of degree n, and they both take equal values. Okay, for more than n distinct values of x. So more than n values of x. If f of x and g of x takes the same values, then we can say that this f of x and g of x are identical. Okay, they are identical. And if f of x equals to g of x is there an equation, then we call it as an identity. F of x equals to g of x is an identity. Okay, just remember the statements only. Okay, no, now if f of x is equals to 0 is a polynomial equation of degree n, okay, and alpha 1, alpha 2, alpha n are the n roots of this equation. Okay, then f of x can be written in this form: a0 is the coefficient of the highest degree, okay, highest degree of x, leading coefficient, also called as leading coefficient, and x minus alpha 1, x minus alpha 2, x. We can write the equation in this form, in the factor form. They are called factors form. Okay, x minus alpha 1, x minus, they are all the factors of this equation f of x. Okay, now I'll just write f of x. You can write f of x in this form: a0 x to the power n. I think you know these things because we have learned in our previous chapter, polynomials, plus a n minus 1 into x plus n. This is the algebraic equation. Okay, where a0 is the coefficient of or leading coefficient, or coefficient of highest degree of x. Okay, now there are few definitions like, if alpha 1, alpha 2, alpha r, they are all equal up to r, then f of x can be written as a0 into x minus alpha 1 over to the power r g of x. Okay, because all the roots are equal up to r, alpha r, so over to the power r square, sorry, power in r. Okay, so this means that alpha 1 is a root, and this root is called multiple root, okay, of order r. Okay, it is called a multiple root of order r, and if there is no multiple root, then we call it the root as a simple root. Okay, now if f of x equals x minus alpha to the power 5x, okay, because f of x is of degree n, then you can write like this: if alpha is a multiple root of order r, then this 5x is a polynomial, its degree is always n minus r, because r is here and the remaining is n minus r. Okay, and phi of alpha not equals to 0, because phi cannot be alpha cannot be the root of phi, because alpha is the root of only this x minus alpha to the power r. Okay, is that clear? Phi of alpha not equals to 0. Okay, now these are all the results. Okay, if f of x is equals to x minus alpha to the power r phi, that is alpha is a multiple root of order r, then alpha is a multiple root of order r minus 1 of f dash of x. F dash of x means derivative of f dash. Similarly, you can from here you can also write the result that f double dash, okay, not f double dash, alpha is a multiple root of order r minus 2 of f double dash of x is equal to 0. Okay, and similarly, you can write in this way that f alpha is a root of simple root. Okay, alpha is a simple root of f r of x. R means rth derivative. Okay, if you do the rth derivative, you get just simply alpha is the root of rth derivative of f r of x equals to 0. Okay, this thing you can do yourself also. Okay, now there are few examples in your book also. You just go through it. Okay, I can send you the this things of book, PDF file of book also. Okay, now there are few still results like okay, now if there is one equation, okay, with real coefficients, okay, real coefficients. Now if alpha plus I beta is one root of this equation, okay, then its conjugate, then alpha minus I beta is also the root of this equation. That means complex roots, they are complex roots actually, okay. Then complex roots always occur in conjugate pairs. You know conjugate pairs, okay, alpha plus I beta and alpha minus I beta, they are conjugate pairs, okay. So complex roots always occur in conjugate pairs. Remember that, okay. Okay, you don't need all the proof of these things, okay. Similarly, okay, there are lots of examples. I will send it to you. You just go through it. Similarly, the surds. You know surds, that if alpha plus root over beta is one root of the equation, given equation with real coefficient, then alpha minus root over beta, these are also conjugate pairs. If alpha plus root beta is one root, then alpha minus root beta is also another root of the given equation. That means surd roots, they are called surds. You know surd, okay. Surd roots also occur in conjugate pairs. Now there are some important theorems that we need to remember all these things, okay, like theorem, okay. If f of x be a polynomial with real coefficients, okay, and f of x equals to 0 be one equation, and I think we have done these theorems in our differential calculus part also, okay. If alpha and beta be two real distinct real numbers, okay, alpha and beta are two real distinct real numbers, such that f of alpha into f of beta is always negative. You know those things, okay, they are in opposite signs. F of alpha into f of beta are of opposite signs. Then the equation this has at least one real root between alpha and beta. Then f of x equals to 0 has at least one real root between alpha and beta. Okay, so if we check these things geometrically, then f of alpha and f of beta, suppose this is alpha and this is beta, and f of suppose alpha is positive, then f will go over here, and if beta is negative, then f will go below. Then if we join this, there can be many crossing of x-axis. So the crossing part, these are the roots. Okay, there can be a single crossing also, or there can be more than one crossing of the polynomial f of x crossing at the x-axis. Is that clear? I think you have done these things in differential calculus also. I think it's not so hard for you to know all these things. And in numerical analysis also we have done these things. Okay. Now if f of x keeps the same sign, suppose f of x keeps the same sign, suppose f of alpha into f of beta keeps the same sign, either plus plus, either minus minus, then what is the possibility is that then f of x has no real root, then f of x equals to 0 has no real root, and conversely also it is true. Okay, has no real root. Okay, now this is just a corollary part. Now there is one general theorem combining this and this. Okay, that one is important. Now if f of x equals to 0 be an equation, and f of x be a polynomial with real coefficients, and alpha and beta be two distinct real numbers, if f of alpha dot f of beta is negative and they are of opposite signs, then this equation f of x equals to 0 and you get at least one real root, but in this case we can say that f of x has odd number of real roots. F of x equals 0 has odd number of real roots, either 1, either 3, either 5, either 7 or 9, depending upon the degree of f of x equals to 0. So f of x equals to 0 has odd number of roots. Okay, so this is important. Now geometrically also we can prove this one, that alpha beta, suppose alpha is this, beta is this, f of alpha is this, f of beta is this. Now if you want to reach beta, draw f of x, then one crossing. Okay, suppose this. How many crossings? 1, 2, 3 crossings. So the crossing is odd always. You will never get an even crossings. Remember that. Okay, in this case 1, 2, 3, 4, 5, 6, 7 crossings. So you will never get even crossings. You will always there will always occur odd number of crossings. That's why odd number of roots. But if f of alpha and f of beta are of same sign, but if f of alpha into f of beta is greater than 0, they are of same sign, then f of x equals to 0. What was in this theorem corollary? What was there? That f of x equals to 0 has no real root. So in this case also f of x equals to 0 has no real root, either no real root or even number of real roots between alpha and beta. You can say real root, even number of roots. Just simply write, say even number of roots. Okay, even number of roots. So I'll give you also geometrical. This is alpha, this is beta. Either f of alpha, f of beta is f of alpha and f of beta, they are at the same side of the axis. Okay, either above the x-axis or below the x-axis. Suppose f of x to f of x, no crossing, that means no root. Suppose if there is a crossing, then there must be two crossings. Okay, so even 1, 2, 3, again 4 crossings. So always you have to perform even number of crossings, hence even number of root. So this theorem is very important. Remember this statement. You don't need a proof. Okay, in case if you need a proof, then I will just go through it. It's a simple one. Okay, you can also check yourself. If it is not possible for you all, then you can just ask me. Okay, I can tell you the whole proof also. Okay, so this was our theorems. Okay, there are a lot of examples also. Okay, just go through it. Okay, now next is Rolle's theorem. You know Rolle's theorem? You have learned Rolle's theorem in differential calculus also. So over there, Rolle's theorem for algebraic equation, and there was a different statement of Rolle's theorem. The same statement we are going to introduce here. What is Rolle's theorem? What Rolle's theorem says, this is important. Okay, remember this theorem statement. Let f of x be a polynomial with real coefficient. F of x be a polynomial. Okay, ROLLES. Be a polynomial with real coefficients. Okay, between two consecutive real roots of f of x equals to 0. Between two consecutive between two consecutive real roots of f of x equals to 0. So between two consecutive real roots of f of x equals to 0, there is at least one real root of f dash of x equals to 0. Okay, so between any two consecutive real roots of f of x equals to 0, there is at least one real root of f dash of x equals to 0. So this is Rolle's theorem. Okay, remember the statement. You don't need all the proofs of this. Okay, so there are some corollaries. Okay, or corollaries of this theorem. Okay, so we'll just state some of them. Okay. Between corollary between two consecutive roots of f dash of x is equal. Suppose alpha dash and beta dash are two consecutive roots or real roots of f dash of x equals to 0, then there exists no real root. Okay, there exists no real root, or at most one real root of f of x is equals to 0. So this is one important result. Okay, so between two consecutive real roots of f dash of x equals to 0, there exists no or at most one real root of f of x equals to 0, and that root must be simple. Okay, that must be a simple root, not a multiple root. Okay, suppose instead of 1, okay, suppose there are two roots alpha and beta between alpha dash and beta. Suppose there is according to this corollary, it was said that there are two real roots of f of x equals 0. Okay, one real root, but let us suppose that there are two real roots. Okay, then by this Rolle's theorem, between two consecutive real roots f of x, there is at least one real root. Then between alpha and beta, there exists one real root, gamma dash. Okay, according to the Rolle's theorem. So that means alpha and beta dash are not consecutive roots. There is again gamma dash. So which is a contradiction. Clear? That's why there exists only one real root between alpha dash and beta dash of f of x equals to 0. So this is the logic between this result. Okay. Suppose f of x is equals to 0. This is another one theorem. Okay. Suppose f of x equals to 0 has r real roots. R real roots. Okay, then the number of real roots of f dash of x equals to 0 is r minus 1. Okay, is that clear? Okay, I think these things are simple. Okay, now the important thing from this chapter is Descartes' rule of sign. Descartes' rule of, it's easy. Okay, it gives the number of real roots, number of positive roots and number of negative roots. Okay, the number of positive roots of an equation this with real coefficient does not exceed the number of variations of sign in the sequence of the coefficients of f of x, and if less, it is less by an even number. Okay, I will write the number of positive roots of an equation f of x equals 0 with real coefficients does not exceed the number of variations of sign. Exceed the number of variations means changes in sign. Number of variation in changes in sign. Plus to minus, minus to plus. Okay, change in sign in the sequence of the sequence of the coefficients of f of x. Okay, the coefficients of f of x, the sequence of coefficients, whatever the question has given, like in this way, this sequence a0 x to the plus n plus a1 x to the n minus 1 plus a2 x to the n. You can't check the variation of sign in like this one, x to the power 4 plus x cube plus x square. You cannot change the change of sign in this type of equations. You have to make a standard sequence like this. Okay, then only you can check the variation of sign. And if does not exceed, okay, if number of variation is 2, then the number of positive root is 2. And if it is less, then it is less by an even number. If it is less, it is less by even number. Suppose number of variation is 4. Okay, so number of positive root is either 4 or 2 or 0. Is that clear? Okay. Similarly, for negative roots, you have to check number of variations in sign in the sequence of coefficients of f of minus x. Okay, and over here you will get the number of negative roots, and in this case also, if it is less by an even number. Okay, suppose degree is 8. Degree of the given equation with real coefficient is 8, and number of variation of signs are given for positive root 4 and for negative root 2. Then total it is 6. So what can be the remaining 2 roots? Okay, also 4 is the maximum. It can be either 2 or it can be 0 also. And in this 2 is maximum. It can be either 2 or 0. So what will be the remaining number of root? The question is like that. Okay. Then the remaining is actually the imaginary root. And remember that imaginary roots are always occurring conjugate pairs. So either there are 2 imaginary roots or 4 imaginary roots or 6 imaginary roots. So the remaining number of roots is always complex. Is that clear? Okay, so this is the this is our chapter. I don't want to go through the examples today. Okay, you just check yourself. Okay, examples in our next class, or if possibly next class, or maybe I have to make another video because I'm having some problem with the laptop. So I can give you some sums also, and I can send you also exercises also. Okay, you just try yourself. Okay.